Friends, welcome to the Essentials of Inorganic Chemistry. I am your friend Dr. P.D. Bhatt. In this present series entitled Quantum Mechanics, I am going to teach some topics of quantum mechanics which are generally taught at the postgraduate level. This is the first talk in this series, and today I am going to discuss commutation relations, angular momentum, operators, and their commutation relations. Friends, there are some prerequisites to understand this topic, and therefore I will brush up some of the topics that you might have learned at the undergraduate level. To begin with, we'll take the case of angular momentum. What is angular momentum? By definition, the angular momentum of a particle moving around a fixed point is the vector product of its radius and linear momentum. Friends, from the definition, we should focus on these last words: moving around a fixed point. Moving around a fixed point. So the motion is not a linear motion, it is an angular motion. It may be a circular motion. Then comes into the picture a property called angular momentum. Otherwise, you have a property called linear momentum. So now assume that a particle is moving around a fixed point on a circular path, and the radius of the circle that is created is r. Then the angular momentum is defined as r cross p, where p is the linear momentum. Capital L is the symbol for your angular momentum, and P is the symbol for your linear momentum. Now, the angular momentum will have three components corresponding to the three coordinates x, y, and z. So, you will have three quantities Lx, Ly, and Lz, where the component Lx is defined as y multiplied by pz, that is the z component of the linear momentum, minus z, that is the position, multiplied by the y component of the linear momentum. So Lx is equal to ypz minus zpy. Here you will see that you are talking about the x component of the angular momentum, but when you equate it, there is no x seen in the equation. It is ypz minus zpy. In the same way, the y component of the angular momentum is given as zpx minus xpz, and the z component of the angular momentum is given as xpy minus ypx. So these are the basic equations for the components of angular momentum. Now there is one important property of angular momentum that also I think you should keep in your mind, and it is L square, that is the square of the angular momentum, is equal to Lx square plus Ly square plus Lz square. Immediately this property may not be very important to you, but as the lectures progress, you will understand that this equation will help us in making many other important derivations. Now, we have already seen that Lx is equal to ypz minus zpy is your x component of the angular momentum, but you have to have an operator corresponding to the components of angular momentum. In order to understand that, here also we will go little behind. We will first see how the operator corresponding to the component of linear momentum was derived, and then we will go to the angular momentum. So in order to set up an operator for linear momentum, what we do is we go back to the Schrodinger wave equation for a wave traveling in one dimension, and this one is the equation that we all are familiar with: d square psi by dx square plus 8 pi square me upon h square psi is equal to 0. I can reorganize this equation in such a way that the E psi term comes on the right hand side. So it will appear like this: the h square will go to the numerator with a minus sign, and this 8 pi square m will go to the denominator, and then it gets multiplied with d square psi by dx square, which is equal to your E psi. Now some of you might be knowing, but for those who are not aware of, I will introduce a term h cut. This h cut is equal to h by 2 pi. So sometimes we will be writing h cut and sometimes we may write h by 2 pi. So the same Schrodinger wave equation using h cut instead of h by 2 pi can be written as, in place of h square upon 4 pi square, I am writing h cut square, and therefore in the denominator you will be left only with 2m. So this equation will be like minus h cut square upon 2m d square psi by dx square is equal to E psi. This is also your Schrodinger wave equation. It is just a different form. Now you know that the total energy is equal to kinetic energy plus potential energy. But when you are having a wave traveling in only one dimension, say x, then the potential energy remains constant. It is as if a marble is moving on a floor. Then what happens? As long as the marble doesn't leave the floor, the potential energy will remain constant. You know, potential energy is energy because of position. In case of marble, you can say energy because of height. So if the marble is not moving at all in z direction, then its height will not change, and therefore V will remain, V, that is the potential energy, will remain constant. And for mathematical simplicity, this potential energy is considered as 0. So therefore in the Schrodinger wave equation, here you write E psi, otherwise it should be E minus V psi. If it is a three-dimensional, if it is a wave traveling in 3 dimension, then you will have to write E minus V psi. But for 1 dimension, E psi is okay. Now this E is your kinetic energy. I already told you that E is the kinetic energy and V is your potential energy. The kinetic energy can be equated as 1/2 mv square. This is yet another way of writing 1/2 mv square upon 2. Now what I do is I multiply the numerator and denominator by m. So it becomes m square v square upon 2m. And now I know that m into v, mass into velocity, is equal to momentum. So m square v square is equal to p square. So this term becomes p square upon 2m. Kinetic energy is equal to p square upon 2m. And on the other hand, we know that the kinetic energy is equal to this. So I will say p square upon 2m is equal to minus h cut square upon 2m d square psi by dx square. And then finally I will say p square is equal to minus h cut square upon d square psi by dx square. Now I have got some equation for p square, but it is in minus. You cannot get minus value for square of any number. The square of minus 1 is 1, but there is no number for which the square is minus. So for that you have to use the concept of complex numbers, and therein I square is equal to minus 1. So what we do is, this equation p square is equal to minus h cut square upon d square psi by dx square can be factorized as minus I h cut d by dx multiplied by minus I h cut d by dx. So my I square is equal to minus 1, so it becomes minus h cut square upon d square by dx square, and therefore then you can say that if p square is equal to this multiplied by this, both are same, then p is equal to minus I h cut d by dx. So this minus I h cut d by dx is your operator for the linear momentum for a particle, for a wave traveling in one dimension. Now this linear momentum, which is generally expressed as px is equal to m into vx, is represented by an operator this, that I have already shown you, particularly in quantum mechanics. But if the wave is traveling in 3 dimensions, then this d by dx will become delta by delta x, because it becomes a partial derivative. So for px you will have the operator minus I h cut delta by delta x. This I assume you have already studied. Now we come to the angular momentum. The angular momentum Lx is equal to ypz minus zpy. We already know this. What we are going to do is, in place of pz, we are going to put the z component of the linear momentum operator. So you will see that the operators corresponding to the x, y and z components of angular momentum will now look like this: h upon 2 pi I y delta by delta z minus z delta by delta y. And in the same way you can have the operators for the y component and z components of the angular momentum. Now once again, the term h by 2 pi is also written as h cut, and if you are using atomic units, then this h by 2 pi is going to vanish. So what we will be doing is that when we actually use these operators, then instead of writing h by 2 pi I will be writing 1 upon I, because I am using the atomic units, and while using the atomic units, this h by 2 pi is not to be mentioned. Now comes commutator. Mathematically, when we say commutator AB, then it has to be shown like this: square bracket A comma B bracket over. This means commutator AB, and commutator AB is equal to A multiplied by B minus B multiplied by A. This commutator property is extremely important in quantum mechanics. Why? I will explain you the significance of commutator. Say if A and B are the two operators for two physical properties, and if you find that commutator AB is equal to 0, then it means that the two properties corresponding to these operators A and B can be determined simultaneously. So it is about the Heisenberg's uncertainty principle. If commutator AB is equal to 0, then you can determine the properties corresponding to A and B simultaneously. But if you find that the commutator is not equal to 0, then the Heisenberg's uncertainty principle will be followed and you will not be able to determine the two properties simultaneously. So very clearly you can make out that if you recall the Heisenberg's uncertainty principle, it is said that it is impossible to determine the position and momentum of a microscopic particle simultaneously. So it means that if you take commutator x px, then it will not be equal to 0. Because if it is equal to 0, then x and px can be determined simultaneously. So that is the importance of the commutator. Now we come to the main point. The angular momentum operators and their commutation. We will take the commutator property of x and y components of angular momentum. So ahead we are going to evaluate commutator Lx Ly. Friends, it involves tedious mathematics, and those who do not have strong mathematical background may not be able to understand this derivation easily from books, and that is why what I have done is I have simplified the derivation as much as possible, though it has become lengthy, but for the first time, for better understanding, this exercise needs to be done, and afterwards you can club certain steps and shorten the derivation. So let us take a look at the derivation. We want to evaluate commutator Lx Ly, and we know that it is equal to Lx multiplied by Ly minus Ly multiplied by Lx. But we know that in atomic units Lx is equal to 1 upon I y delta by delta z minus z delta by delta y multiplied by this Ly, that is 1 upon I z delta by delta x minus x delta by delta z. So you have two terms, 1 upon I and 1 upon I. So it becomes 1 upon I square. So I am clubbing up them 1 upon I square with an understanding that I square is equal to minus 1. So it will be 1 upon minus 1, and that is equal to minus 1. So this equation will now look like this. Minus 1 multiplied by, now I am putting the first step of the derivation. What I am going to do is y delta by delta z multiplied by z delta by delta x. See, y delta by delta z multiplied by z delta by delta x minus, now y delta by delta z multiplied by x delta by delta z, and as this x is carrying the minus sign, it will be minus y delta by delta z multiplied by x delta by delta z. So first I have multiplied both these terms with y delta by delta z. Next I will multiply both these terms by minus z delta by delta y. So it becomes minus z delta by delta y into z delta by delta x plus z delta by delta y into x delta by delta z. Why this is plus? Because you have minus and another minus, therefore it becomes plus. Now again you have got two terms in the bracket, and what you have to do is you have to perform a partial derivative. So it is like partial say delta by delta z of a multiplied by b, then you will say it is equal to b delta a by delta z plus a delta b by delta z. What I do is, first I will take the partial derivative of z, keeping this one constant, and then I will take the partial derivative of this, keeping this one constant. So how do I write? Y, it is already there, it is outside, delta by delta z, I have taken out this delta by delta x on the left hand side, and I am taking the partial derivative of z first. So it is delta by delta z of z. Then y is already there. This time I am not taking derivative of z, so it is yz, and delta by delta z is already there, and now I am taking the derivative of delta by delta x. What I am doing is I am taking delta by delta z of delta by delta x. So this is how the first term will split into two. In the same way the second term will also split into two. It becomes, once again I will show you, and then I will leave the remaining for your understanding. What we do? Minus y remains as such. Delta by delta z, this delta by delta z comes on the left hand side, and then I take delta by delta z of x first. I am going to take delta by delta z of x and delta z one by one. So first I take delta by delta z of x, keeping delta by delta z constant. Then I keep x constant and take delta by delta z of delta by delta z, and that is how I write the entire equation. Now what happens? You have to understand that how I get these values. See, look at the first term, y delta by delta x into delta z by delta z, which is equal to 1. You can also say delta z by delta z cancelled, therefore 1. Or else you can say that delta by delta z of z is equal to 1. So this term becomes y delta by delta x of 1, or rather y delta by delta x multiplied by 1. Then the second term, yz, now you have delta multiplied by delta, so it becomes delta square, and then you have delta z by delta z multiplied by delta x, so it becomes delta z multiplied by delta x. Next step is little important. See, minus y delta by delta z of 0. How this 0 comes? It comes as the value of delta by delta z of x. When you are taking partial derivative with respect to z of x term, then it is considered as a constant. It is considered like as a number. Say what will be partial derivative of 3, then you know it is 0. So x, the partial derivative of x with respect to z is equal to 0. Therefore here you will find the term 0. Then similar things will come, minus yx you have delta square, and this time in the denominator you have both delta z, therefore delta z square. Then you have minus z delta by you have this term becomes 0, delta z by delta y is 0, so your delta by delta x of 0, and then this progresses. If you apply your mind in the same way, then you will be able to derive this part. So what happens? Any number multiplied by 0 becomes 0, and therefore this term, and this term, 3 terms will become 0 and they will be removed. So I will write minus 1. Now this 1 I don't need to write, because anything multiplied by 1 is the same number. So y delta by delta x plus yz delta square by delta z delta x minus this one yx, because this term is 0, minus yx delta square by delta z square minus, then comes this term is 0, here it comes minus z square delta y by delta x plus zx delta square by delta y delta z. Now I have minus 1 outside the bracket, and therefore just for the sake of mathematical simplicity I am changing the signs of all the terms that I have derived, and I am removing minus 1. So this is minus y delta by delta x and so on. So this is the value of Lx multiplied by Ly. This is not the value of commutator Lx Ly. See, I go back to the original relation. We are evaluating Lx comma Ly or commutator Lx Ly. Commutator Lx Ly is equal to Lx multiplied by Ly minus reverse Ly multiplied by Lx. But since the derivation is very long, what I have done is I am first evaluating just Lx Ly. See, I have equation only for Lx Ly. Now I will do similar exercise for Ly Lx, and then I will subtract Ly Lx from Lx Ly and see what is the value. So I come back here. This was the last equation we derived. This is equal to Lx Ly. Now Ly Lx, we again know it is 1 upon I, and since it is Ly, it is z delta by delta x minus x delta by delta z multiplied by the x component. Again this I becomes I square, and eventually it will become minus 1, you know that. And first what I am going to do, the first step, I will multiply this z delta by delta x with y delta by delta x, and then z delta by delta x with minus z delta by delta y. So in that way I will be getting 1, 2, 3 and 4 terms. So this is relatively simple mathematics, so I am not explaining you term by term, but what you have to do is you have to multiply the quantities in the second bracket with the quantities in first bracket one by one. So we will take first and first, then we will take first and second, then we will take second and first, then we will take second and second. So that is how it comes. Now in place of I square I am writing minus 1, 1 upon minus 1 is equal to minus 1, and therefore this will be the term. Now what happens? This is the trickiest step, because what happens? This time you are taking derivative, partial derivative of a term like AB. So it has to become like AD by dx, B plus B. You know, you have to take the derivative one by one while keeping the other constant. So how do I do that? Z delta by Z delta by delta, just a moment, z delta by delta x multiplied by 0. How does this come? Because you know I have skipped one step. When you take delta by delta x of y, then it is equal to 0. So it is z delta by delta z. This delta by delta z is moved over here, and I have straight away written the result of delta y by delta x, that is equal to 0. I have skipped one step, but if you are not able to understand, then you have a similar step which is given in the Lx Ly. So you will be able to compare it and understand. Now what I do in the next step, I have z, I am bringing y out, and then I have delta square by delta x delta z. Then again I have minus z, I am bringing delta by delta y outside, and I know that delta z by delta x is equal to 0, therefore I am writing 0 over here, and in the same way I am writing the entire equation. At some place I am getting 1 also, but we know how we get this 1 and zeros. So what happens again, from this 1, 2, 3, 4, 5, 6, 7 and 8 terms, you will be removing 1, 2, 3 terms, because they are all multiplied with 0, and you will be left with 5 terms, 1, 2, 3, 4 and 5. And I am changing the signs of each of the terms so that I can remove minus 1. So it becomes minus zy, this term. This is already 0, so I don't have to mention it. It becomes minus zy delta square by delta x delta z, and then this is also 0, because plus z square, and then this is 0. So you have again xy plus xy delta square by delta z square, and so on. So this is the value for Ly Lx. Now I am in a position to evaluate the commutator Lx Ly, because I have the values of Lx multiplied by Ly, and I also have the values of Ly multiplied by Lx. So I can find out the value of Lx multiplied by Ly minus Ly multiplied by Lx. So for doing that, I have simply, what I have done is, I have copied and pasted the value of Lx Ly, and then I have put a minus sign over here, and then I am putting a large bracket and putting the value of Ly Lx. So once again these signs are going to change, because this minus minus will become plus, minus plus will become minus, and so on. But this is going to be relatively easy step. So once you write down, here it will contain 1, 2, 3, 4, 5 and another 5, means you have got 10 terms. But when you evaluate this, you will see that leave the first term, come to the second term, minus yz delta square by delta z delta x. You will find out something having plus yz, and you will see that it will get cancelled. So this is your plus yz or plus zy, and again you have got delta x delta z. So these two terms, this second term and this zy term, will be cancelled. In the same way, this yx term will be cancelled with this xy term having delta z square at the denominator. Then this z square term will be cancelled with this minus z square term, and then you will be left with xz. This minus zx term will be cancelled with the last term plus xz term, and this term will remain. So out of these 10 terms, you will be left with only 2 terms, that is the first one and the last but 1. So it comes to be equal to x delta by delta y minus y delta by delta x. Now this is the value of your Lx Ly minus Ly Lx. This looks little bit like Lz, x delta by delta y minus y delta by delta x. But then this I, 1 upon I is missing. So this is actually I multiplied by Lz, that is what we can say, because 1 upon I is missing over here. So in atomic units you can say that Lz is equal to 1 upon I x delta by delta y, this we know, and therefore you will say that Lx multiplied by Ly is equal to this, which is equal to I multiplied by Lz, because if I put 1 upon I over here then only it will become Lz, but I am not putting it, therefore this I will go on this side. So Lx multiplied by Ly is equal to ILz. The primary learning from this is that the x and y components of the angular momentum do not commute, because it is not equal to 0, it is equal to ILz. This also means that you cannot determine the x and y components of the angular momentum simultaneously. Now, this derivation was tedious, but it was not really great difficult. So with the understanding that I have already provided, particularly the mathematical understanding in the first example, you can easily calculate the commutator Ly Lz, and you know that the answer is going to be ILx, because commutator Lx Ly is equal to ILz. Therefore commutator Ly Lz is going to be ILx. And in the same way you can also calculate commutator Ls Lz Lx, that is going to be equal to I Ly. Now there is one interesting thing, that you have seen that x and y components of angular momentum do not commute, it is not equal to 0, but for linear momentum it is going to be 0. It is a very short description, I will show you. Say if you take the x component of linear momentum and y component of linear momentum, that is px py, then the commutator will be given like this. Px is equal to minus I h cut delta by delta x, and py is equal to minus I h cut delta by delta y. So this is commutator, say AB, which is equal to A multiplied by B minus B multiplied by A. So this is minus I h cut delta by delta x multiplied by minus I h cut delta by delta y minus, this is your AB, now you are taking minus BA, minus I h cut delta by delta y multiplied by, this dot stands for multiplication, minus I h cut delta by delta x. So what we do is, we will take away the minus I h cut outside, and this term becomes delta square by delta x delta y, and then you have this time you have two minus signs, therefore it will become plus I h delta square by delta y delta x. So both these terms are equal and opposite, and therefore the addition will give the value 0. So that is how the components of the linear momentum, they commute with each other. So I will call it a day for this lecture. I will end it over here, but I will be definitely adding more lectures. Particularly, these lectures are related to many electron systems, and the topic is generally taught at the postgraduate level. There are some good textbooks which can be used. I can name the authors, I do not remember the name of the books, but one of the book is by A.K. Chandra, then the other one is Peter Atkins, the other one is McGuire Donald, and a book by Ira Levine is also a very good book to study this quantum mechanics relating to many electron systems, which is generally taught at the postgraduate level. So we'll meet again. Till then, goodbye. Thank you.